We are ready for section 2C, talking about the states and the phases of matter, the three main types that are very commonly found within the Earth's atmosphere: solids, liquids, and gases. We'll mention plasma near the end of this session, but we'll focus on the solids, liquids, and gases, and in the next set of notes, we'll talk about the phase changes, such as what happens to the molecules or atoms when a substance melts from a solid into a liquid. But right now, we're just going to define the phases of matter. Are we ready to begin? All right. Particle motion. Remember that molecules and atoms, even if the object you're looking at appears to be completely stationary, the particles that make up that substance are always in motion. We defined this before as Brownian motion. Look at the pictures there. The gas particles, the liquid particles, and the solid particles. They're always moving, although you can't really see that in the picture. But the placement, the arrangement, the amount of energy, and the speed at which the particles are moving are very much going to combine together to give us the phase of matter that any piece of matter is in. But Brownian motion again says all particles are constantly moving. Here are the four main states, once again: solid, liquid, gas, and plasma. We're not going to focus much on plasma in this class. We'll define it a little later, but we're going to concentrate a whole lot more on the three main phases of matter found within the Earth's atmosphere: solid, liquid, and gas. Water. Here is evidence that God knows what he's doing. Water is the most abundant resource in the Earth's atmosphere. It's also the one substance that every living organism must have in order to survive and live. And water is also found in all three phases in the Earth's atmosphere naturally: solid, liquid, and gas. H2O, you'll hear me refer to the chemical formula and the chemical name for water quite often. Dihydrogen monoxide, that comes from the 2 on the H and the unwritten 1 on the oxygen, dihydrogen monoxide. But water, as you see on the screen there, exists in all three phases of matter simultaneously in the Earth's atmosphere. Ready? The states in the particle model, the state or the phase of matter, they're called either state of matter or phase of matter. That's determined by the amount of kinetic energy of the particles. Let's define kinetic energy a little bit better. Kinetic energy is energy of motion, and for particles to move, they have to have kinetic energy, and many times that's in the form of thermal energy, but not always. But particles are always going to have some kind of energy. The amount of the energy and the proximity of the particles to each other, they're going to help determine the phase of matter. For example, in a solid, the kinetic energy is less than the attractive forces among the particles. All particles have attractive force, and we'll study that in a later chapter. But every object and every particle has a gravitational attractive force on every other object. And in a solid, the amount of kinetic energy the particles have is weaker than the force. That's what the less than sign is for. So the less than sign, we're talking about a weaker force in that case. The energy is weaker than the force that are pulling those particles together. In a liquid, some of that kinetic energy is greater than the attractive force. So particles gain more energy by adding heat and kinetic energy. Those particles start to move a little faster and a little bit further apart. And when the amount of that kinetic energy gets larger than the attractive force or greater than, then these particles are going to start to flow. I like to say this: when we feel very low energy, we like to sit down and just take it easy and not move around a whole lot. As we start to feel more energetic, we start to get up and wander around a little bit, and in that case we're moving a little faster and we start to spread out from each other a little more. When we all feel very energetic, That's when we want to run. We want to move much faster, and we tend to spread more and more apart from each other. And now that liquid is becoming a gas. The kinetic energy of the particles is far greater than those attractive forces that are trying to hold the particles together. In this case, watch little kids on the playground. They love to run around. And as we run around, the faster we get, the further apart from each other we get. Those particles move very fast and in much more randomized motion. In a solid, the particles are very, very, very close together. And if there's any motion at all, it's a very small, fixed, repeating pattern that goes constantly. In a liquid, the energy gets greater, and then the particles start to flow and move in more random directions. And in a gas, those particles have a lot more energy, much greater than the attractive force, so the particles can move much faster and much further apart in a gas. Ready? Now, a little bit more about each phase of matter in some detail. In a solid, you've heard this a lot. Solids all have a definite volume and a definite shape. Remember, volume is the size, the amount of space the piece of matter takes up, and the shape, of course, what does that object look like? We'll talk a little bit more about solids and about changing the shape of them, but typically they're not going to change their shape on their own. You leave a block of wood sitting on the table, well, both the table and the wood are solids, they're going to maintain their shape. There's a small amount of motion, low Brownian motion in the particles of the phase of matter called a solid. And again, that motion would be very, very small amounts and in a very fixed, repeated pattern. So much so that unless you had a really powerful microscope, you probably wouldn't even notice the motion just by looking with your own eyes. You'd have to have a good electron microscope to notice any motion at all in a solid. The atoms are packed very, very, very close together, making it very difficult to change the shape even by adding some pressure. Now, there are some solids, such as clay or Play-Doh or a Nerf football maybe, that we can change the shape simply by applying some pressure, and more about that is coming up in a moment. Low compressibility, that means we cannot take a solid and squeeze those molecules closer together. They're already as close together as they're going to get. So low compress, as we're trying to press and compress things together, we don't have that ability. So in a solid, there's low compressibility. Ready? Started to mention this a moment ago. In a crystalline solid, that's what we think of a lot when we say solid, very, very rigid, like this podium that I'm tapping on. It's extremely difficult to change the shape, if not impossible, of that podium without ruining the podium. That's because the molecules are very, very close together. And those kinds of solids are crystalline. Particles in a very fixed, repeated pattern of motion, so close together that even with a large amount of pressure, we're not going to be able to change the shape. I mentioned things like Play-Doh and clay and Nerf footballs a few moments ago. Well, those are things that we can squeeze together. Think of a cushion or a pillow. You can squeeze and kind of reshape that amorphous solid. Here we go with the root word morph, which means change. So even though these solids may not change their shape on their own, by adding some pressure, and usually not a whole lot of pressure, a nice small amount, we can change the shape. And sometimes the shape will stay the way we put it, or other times the shape, once we stop squeezing something like a Nerf ball, will return to the original shape. Modeling clay or Play-Doh, that will stay in the new shape. And you may have noticed when you use clay or Play-Doh, as that substance gets warmer by absorbing kinetic energy from our hands, then those molecules are easier to move apart. So you take a good piece of modeling clay right out of the package, it will start off feeling more like crystalline, but as we mess around with that in our hands, then the molecules warm up and start to move further apart, and that's what makes the clay and other similar substances amorphous. Ready? In a liquid, such as water, I drink the water, we have a definite volume but not a definite shape. We pour the liquid from one container into another, from a tall glass into a short but wide bowl. We'll keep the same amount of water, kind of disregarding the tiny droplets that may stick to the glass when we pour, but we're going to get the same amount of water but in a much different shape. Liquids have definite volume. If I pour 10 milliliters of water into a much different shape of container, I'm still going to get 10 milliliters of water, but just in a much different shape. Low compressibility. Try pouring some water in your hand and squeezing that water together. You're not going to do so. The water's going to run off the sides of your hand and through your fingers. So liquids have very low compressibility. Even though the molecules are a little further apart in a liquid, they're really not going to get much closer together. Because remember, in the liquid phase, more kinetic energy, these molecules are going to try to spread apart. Liquids, as you already know, take the shape of their container. So whatever we put a liquid in, that is the shape of that volume of liquid. The volume won't change, but the shape will. In liquids, the particles are random, moving in all different directions. They're much more mobile, but still very close together. Nowhere nearly as close as in a solid, however. When those molecules start to gain more heat energy, they'll spread further and further apart, and now you're getting into vaporization and turning into a gas. And that's what our next set of notes will be about. Ready? Some liquids are thicker than others. I like to say, think of a bottle of pancake syrup. Buy that right off the shelf, room temperature, probably fairly easy to pour onto your pancakes. The word viscosity is a resistance to flow. This word gets confused a lot. Viscosity is not how easily a liquid flows. Viscosity is the resistance. Thicker liquids are harder to pour, therefore they have more viscosity. Low viscosity flows easily. Take that syrup, put that syrup in the microwave and really warm it up. First of all, I like to taste better when the syrup is warm, but because it's so full of sugar, I'm not supposed to eat it much anyway. But I warm up that syrup, and that syrup should then very easily pour out of the bottle onto my pancakes. Try this. Put that syrup in the refrigerator overnight. Then in the morning, try to dump that syrup out of the bottle onto your pancakes. That syrup, because of cooling down in the refrigerator, the particles are much closer together, making that syrup much thicker, therefore higher viscosity and harder to pour. Warm up that syrup in the microwave, give those particles more kinetic energy, those particles will spread further apart, thinning out the syrup and making that syrup much easier to pour. Motor oils, you want to have a high viscosity so the oil sticks to the engine parts better and reduces the amount of friction that could wear down those engine parts. So in some cases, we want high viscosity. Cold syrup, probably not, but motor oil, very likely we want higher viscosity. Viscosity, again, is the resistance to flow. Thicker liquids have higher viscosity because thicker liquids resist flow. Ready? Gases. These particles have now gained a much higher amount of kinetic energy, most likely by being heated up. Not always, though, because you can let a liquid, a glass of water, just sit still without adding a lot of heat, and eventually that water will evaporate. It may take a long time, though. Gases also take the shape of the container, but they also fill up the volume. So you have a balloon, you let some of the air out of the balloon, much of the air is going to spread out and push on the insides of the balloon. Sorry, I had to pause for a moment. But those particles will push on the inside of the balloon, and if they apply enough pressure to the inside, may stretch that balloon back out. Gases are going to fill up the container. Now, gases are very highly compressible, and that's because there's a lot of space in between the particles. So much so that we can easily compress those particles back together. And if we do that enough and reduce the amount of energy, we can turn a gas back into a liquid. And again, next set of notes talks more about all that. Gases have the particles spread out and fill up the container. Now, if we let some of that air out of the balloon, of course, those gases are going to be thinned down, and soon there won't be enough pressure on the inside to stretch that balloon back to its original volume. So there is a limit to how far gases can go. And if we put too much gas, then the pressure applied to the inside is eventually going to make that balloon burst, and any other container in which we find gases. We get that pressure up enough, we can burst whatever the container is. Gas particles have been found to move at approximately 1.5 times the speed of sound. The speed of sound on average is approximately 690 miles per hour. 1.5 times that is around 1,035 miles per hour. These gas particles typically move at approximately that speed of 1,035 miles per hour. Now you get billions of gas particles moving at 1,035 miles per hour. Again, think of the inside of the balloon. Eventually you're going to build up enough pressure, and the more gas molecules and particles we add to that balloon, continue to blow up that balloon, eventually that balloon will burst. That'll happen with tires as well. That's why when we inflate the tires on the car, we have to make sure we don't overinflate, go beyond the limit, pounds per square inch, because that pressure, when the tire pushes on the road pushes back on the tire, and the molecules on the inside are pushing their way out and may eventually burst that tire. So watch the gas pressure, make sure you do not overinflate the tires. Ready? Plasmas, again, we're just going to define what these are. We're not going to worry too much about plasmas. We're talking mainly about solids, liquids, and gases. Plasmas are actually, though, the most common phase of matter in the universe, but outside the Earth's atmosphere. Inside the Earth's atmosphere, once again, solids, liquids, and gases, there are some plasmas, but we find plasmas mostly in outer space. These have ultra-high temperatures, very, very, very hot gases. The sun is plasma. These are high-energy ions, which simply means the atoms that make up a plasma have electric charges and free electrons that move around very, very, very freely. We'll talk more about that in chapter 3 when we start talking about atoms in the periodic table. But plasmas are extremely hot and may be electrically charged. The sun is actually a star, but the sun is much closer to the Earth than the other stars that we see in the sky. The sun is approximately 93 million miles or 150 million kilometers away from the Earth. And that's really all we're going to worry about for plasmas. Ready? All right, so now you know a little bit of the characteristics of solids, liquids, and gases. Again, next time we're going to talk about changing one into another and what happens to those particles during a phase change. Thank you.